Okay, so I know we're all off on these numbers. This is actually 9.3, 9.3 angles of rotation. Finally, now we are now getting into the algebra 2 stuff. 9.1 and 9.2 dealt with right triangle trig, and that was really just a summary of geometry. So this is where things start to get a little bit more difficult. So bear with me. This is a little bit longer than normal. So before we get into this, let's review a little bit of what you know about angles. Okay, in geometry, angles could have been anywhere. They were in triangles, they were in trapezoids, they were in all kinds of different shapes. But basically, the basic understanding of a triangle is that you have a ray, okay, like this, and then you had another ray that went in another direction. And an angle was formed between those two rays. So in geometry, you just have, two lines connected by the same endpoint, what we call them rays. So in this way, it was two rays that had a common endpoint for made an angle. Now here's why it's different in trigonometry. In trigonometry, we also deal with angles, but it's not the same kind of angles you had in geometry. In trig, you have one single ray, and what happens is the ray then gets rotated. So, it's now up here. So you don't have two rays making an angle. You have a single ray that is rotated in a circle a certain amount of degrees. So a ray that is rotated around its endpoint. And that's how angles are a little bit different. So when we measure angles, it's not necessarily going to make some sort of shape. Sometimes you could have this ray go around multiple times. I mean, it just keeps spinning around and the angle just keeps getting larger and larger and larger and larger. So unlike what you could do here with shapes, there's only so much you can go. I mean, you can only go 180 degrees before you would start, shrinking the angle again. So a little bit different here. We're going to focus on this, obviously. So the initial position of the ray is called, right here, this initial position of the ray, this initial starting side, I guess you could think of it, but it's called the initial side. The initial position of the ray is called the initial side of the angle. And the final position, so wherever this ray ends up turning to, is called the terminal side. Terminal meaning end. Terminal side of the angle. The angle is in standard position. I forgot that I had position already there. The angle is in standard position when the initial side starts on the x-axis like it is here. So you can see here, so you have the terminal side, and we'll do this in your notes, it's like all in color and everything, but the initial side, okay, is where it starts. If that initial side is on the x-axis, like it almost always will be, then it's called it's in standard form, or standard position. And then you have a terminal side, which is where it ends up. And this is the rotation of that ray. Okay. So there's actually two ways that you can do this. The angle can go in two different directions. So it doesn't necessarily have to spin around to the left or what we would say counterclockwise. Sometimes the initial sight can also spin the other way in clockwise form and form an angle. So if the direction of the rotation is counterclockwise, which is like this, like you would normally think that it would go counterclockwise, then it has a positive angle measure. So you can see here how, because it is spinning counterclockwise, it has a positive angle. And then if it spins clockwise, or what we would consider backwards, it has a negative measure, as we can see here, the negative 240. Hopefully yours is a little bit clearer than mine. That's negative 240. Okay. The common okay. All right. The common unit for an angle measures is the degree. Now we'll talk about that there are different ways of measuring angles. This is something that's going to be new for you here. But for now, we always think of the measure of angles in degrees, which is what you're used to. A complete rotation of a ray is assigned a measure of 360. So if the angle were to go all the way around in a circle, we know that if it goes flat, it's 180 degrees. You learned that in geometry. But if it were to continue, again, all the way around, it would be 180 and then another 180 or 360 degrees. Okay. The term coterminal angles, this is a concept here, and this is one of your outcomes, is being able to determine coterminal angles. Coterminal angles are angles that are in standard position, and if they have the same terminal side. So they're considered coterminal, terminal, you can spell, if they have the same size. So here, it's really hard to see on mine, I apologize, but hopefully on your notes it's a little bit easier. But notice here on this is the same angle. So we have the same line here for both of these. But notice that if you go two different directions, so if I go, this way, I have an angle of 150 degrees. But if I go backwards, I have an angle of negative 210 degrees. Both get me to the same point. I mean, if I go this way or I go this way, both of them get me to the same point, but they went different directions to get there. And those are what are called coterminal angles. They're angles that if I go one way or if I go the other way, I still end up with the same side. So coterminal angles are angles at which end at the same point. So, what you're going to be asked like on tests and quizzes are going to be to find a positive and negative coterminal angle for the same angle here. So if I have 90 degrees and I want a positive and negative coterminal angle, here's how that works. So imagine 90 degrees. 90 degrees. Okay, it's a corner of a square. Okay, 90 degrees. If I want to find another angle that would be in the same position, the only way to do that, okay, is think about a clock. If the clock were at 12, there are other times when the clock is at 12, right? What ends up happening when it gets to 12 again? Well, the hand goes around again, and it's at 12 again. Okay, so we can think of the same concept, that if it's at 90 degrees, if I want just another positive angle that finishes right here, just go around again. So instead of 90 degrees, I'm going to keep going around all the way around again, and meet back here. To go in a complete circle, remember, is 360 degrees. So if I want another positive angle that is the same as 90, I would just add 360 degrees. 90 plus 360 would be 450 degrees. That means that if I were to do 450 degrees, 360, and then another 90, I would end up at the same place as 90 degrees. Now, if I would like to have a negative value that is also coterminal, so going in the other direction, think about that. If I'm right here and I would like another angle that is negative, just go around the other way. Or in other words, subtract by 360. So to get a positive coterminal angle, I just add 360. And to get a negative coterminal angle, I just subtract 360. So I'm going to subtract 360 from 90, and I get negative 270 degrees. And that gets me my positive and negative coterminal angles. So we can fill out the rest if you want. Go ahead. I'll do one more, and then you can do the rest. But again, to find a positive and negative coterminal angle for each of these, just simply add 360 and then subtract 360. Negative 27 degrees plus 360 is 333 degrees. Negative 27 minus 360 is negative 387 degrees. And so I get my positive and my negative coterminal angles. And you would do the exact same thing with the rest of these. But this is an outcome. So that one should be fairly easy. Coterminal angles have the same terminal side. They finish the same place. So just going one way or going the other way and finishing at the same place, you simply just add 360 or subtract 360. Flip it over. Okay. Now for the new concept, radians. You might have remembered that when we were going over degrees and we were measuring in degrees, you went to your calculator to maybe check the mode and make sure that the mode was set to degree instead of radian. So, well, what is radian? Radian is another way of measuring angles. And so, why do we use that? Why do we use radians when we have degrees? Radians are used heavily in pre-calc and calculus. They make measuring angles in pre-calc and calculus a lot easier. So that is why we introduce radians here. For those going on and taking pre-calc or even calculus, some of you underclassmen, are going to be seeing this a lot. And so here's your sort of formal introduction into radians. But basically, the definition of a radian is the measure of the angle in standard position whose terminal side intercepts with an arc length of r. Now that's a sort of a lot of jargon there. But basically, and I'll try to explain this as simply as possible, if your radius, let's say your radius is 1, a radian would be the angle that creates an arc length that is the same length as your radius. So this is the arc length. Remember, this is, think back to geometry. The length of this arc. 1 radian is the angle that is made here that makes your radius be the same length as your arc length. When your arc length is the same as 1 radius, you have 1 radian. So a radian of 1 would be 1 radius arc length. And it turns out that a circle, a perfect circle, doesn't actually have quite an equal number of radians. And that's where pi comes in. Okay? Because, and we'll explain this here in a second, because of the way a circle works, the angle that creates 1 radius and 1 arc length is not equal throughout a circle. So you end up with pi. Pi is 3.14. It's what that actually means is that it's three of these. Actually, well, it's more than 3 of these. It's actually 6.28. It's 2 pi all the way around. And I'm getting ahead of myself here. But basically, That's where pi comes from. The whole fact of 3.14 and 2 pi comes from that. So basically, if you think back to geometry, the circumference of a circle is the measure of the length around this circle. The circumference of a circle, the formula, is 2 pi r. Okay? So if we assume, or if we imagine that the radius is 1, so if r equals 1, then, if r is just 1, then essentially r just cancels out because it's just 2 pi times 1. So essentially the circumference equals 2 pi. Well, pi, being that it's 3.14, 2 times 3.14 is 6.28. What that means is that you have 6 radiuses around this circle and 0.28 of a radius. It's not quite an even number. Okay, and that's the way, that's for all circles. So what that means is that there are 2 pi radians in a circle. I know this is getting a little complicated here, but again, just to remind, a radian is the angle at which the arc length is the same length as your radius. So if your radius is 1, that would mean your arc length would have to be 1. That would be 1 radian. Okay? And it turns out if you do this measure and you just hit copy and paste, copy and paste, copy and paste, copy and paste, and get all the way around, you would end up with 6 of these, actually 6.28 of these, or 2 pi. Maybe 1, 2, 3, 4, 5, 6, and like a little fraction left over. And that's 2 pi. So what we're going to do is how do we convert from degrees to radians? Okay. Well, this is going to be important here. So being able to go from degrees to radians. So if you are going from degrees to radians, you'll just simply take whatever degrees you have, and you're going to multiply by pi over 180. Okay. Degrees to radians, whatever you have for degrees, just multiply by pi and divide by 180. Super simple. And that'll give you in radians. Okay, radians are always going to be in terms of pi. So we always want to leave pi in there. So if you have 50 degrees, it'd be 50 pi over 180, and you would just reduce the 50 over 180. You would divide the 50 and 180. Pi always stays. Don't actually calculate pi. Pi actually stays there. You should remember that from geometry. When I go from radians to degrees, I just take whatever radians I get and multiply it by the reciprocal. Instead of multiplying by pi over 180, I'm going to multiply by 180 over pi. And what that does is it just cancels out the pi's so that you don't have pi in your answer. And that's it. So degrees to radians, multiply by pi over 180. Going from radians to degrees, you do 180 divided by pi. Okay, so let's look at what this does. I'm going to get my calculator. You're going to need your calculator here. So we're going to start with changing degrees into radians. And there's a typo here. This should not be 4 through 66. There should be a parenthesis here. For numbers 4 through 6, you're going to write a positive and negative coterminal angle. Okay, so let's start here. This is the easy part, going from degrees to radians. So all you do is multiply. So I take 40 and multiply by pi over 180. Remember what I said. The pi does not go anywhere. And you don't actually multiply by pi and get some crazy decimal. It's just 40 pi and then over 180. And then you're going to reduce this fraction. Now, here's a cool little trick in your calculator, and all calculators do this. You don't need the newer version. The older versions do the same thing. If you take your calculator if you're like, I don't know what 40 over 180 reduces to, or maybe you just don't want to take the time to actually reduce it, your calculator can reduce it for you. So if I do 40 divided by 180, and it's going to come up with some decimal. But if I go to math and then just click fraction, so math 1, math fraction, hit enter, boom. It gives me a reduced fraction. 40 over 180, I just hit equals, it did 0.22222. And then it'll change it to a reduced fraction for me. 2/9, perfect. So this is simply just 2 pi over 9, or 2/9 pi. I could do the same thing here. So again, I multiply by pi over 180, multiply by pi over 180. Remember that pi doesn't actually get calculated here, it just attaches itself. So it's negative 150 pi over 180. And now I want to reduce negative 150. Let me zoom in here, a little better view. So on my calculator, let me make some room here. I can just do negative 150 divided by 180, and then just hit math 1. Enter. Negative 5/6. Perfect. So in here, it already reduced it for me, so negative 5 pi over 6. And notice the pi doesn't actually get calculated, it just sort of is there. So I can let you do 3. I don't need to do that. You can figure that out. Now, what about going from a radian to degrees? Well, it just multiply by the reciprocal. Instead of pi over 180, I'm going to multiply by 180 over pi. And what's nice about this is simply the pi's just cancel out. So I end up with just 3 times 180. 3 times 180 is 540, so it's just 540 degrees. Now it does want me to do a positive and negative coterminal angles. So I'm going to do a positive and negative one. Now the only thing that's you gotta be careful with this is it's such a high number that if I go to add 360, I'm fine. This will give me a positive one. If I add 360 to that, I get 900 degrees. So that would be fine. But when I go to subtract 360, I don't get a negative degree. And so hopefully you can sort of figure that out. So if I do 540 minus 360, I don't get a negative degree. So what do you think you need to do? Just subtract 360 again. There you go, negative 180. And so that'll be my negative. My positive and negative coterminal angles. I actually could have used, I could have subtracted 360 and got 180. That's another positive, but that's it. So let's try this again. Multiply, it says to multiply by 180 over pi. Again, essentially, the pi's just cancel out. And I'm left with 4 times 180 divided by 3. So 4 times 180, I hit equals, then divide by 3, and I get 240 degrees. And then I'm going to find a positive and negative, so plus 360, and a negative, minus 360. If I do 240 plus 360, I get 600 degrees. And if I do 240 minus 360, negative 120 degrees. And so that's it. I mean, you can do the last one there if you want to, but that's that's converting from degrees to radians. Okay, almost done. It's the last page. Zoom out. Okay, arc length. Now this is a pretty pretty basic formula here. It is up here. It might be kind of hard to see. But basically, to find the length of this arc, you're going to use the formula. So this SS refers to arc length. In case you were wondering, it's not really explicit what that is. S means arc length. Your degree is going to be in radians, and this is where it's different than like when you were in geometry. So let me move this up a little bit so I can have room. So arc length is the part of the circumference of a circle. And the formula, which is up there in the top left, is S equals R times theta. And the only sort of caveat here, theta, okay, has to be in radians. Has to be in radians. So if they they give you in degrees, you're going to have to convert it to radians. And then use the formula. So you can imagine what kind of questions I'm going to give you. First of all, we're going to give you one where it's already in radians, and then you'll see that we'll give you some that are in degrees. So here's some examples. So a central angle in a circle with a diameter of 30 meters measures pi over 3 radians. Find the length of the arc intercepted by the angle. So just to sort of draw you a picture of what this looks like, remember central angles, I know we're dipping into geometry, a central angle is the angle that goes through the center. Okay, it's this right here, central angle. Now it gives you a diameter of 30 meters, okay, which is important because our formula actually calls for radius, so you should be able to figure out the diameter or the radius from the diameter. That means that R is 15. And then it gives it to you in radians. So we're just going to plug it in. So S equals R times theta. We have R as 15, and we have theta as pi over 3. And we can multiply those. Remember, pi doesn't actually change. So technically, this is 15 pi over 3. And then you can just reduce the... Pi never gets calculated. Never. Never gets calculated. It's just there. Pi is there. 15 pi over 3, well, you just reduce the fraction. 15 over 3 is 5. 5 pi. So that arc length would be 5 pi. Okay. In a circle with a radius 10 centimeters is intercepted by a central angle of measure of 160 degrees. So we have the radius, but we don't have the angle in radians. So we will need to convert 160 degrees into radians. When we do that, we do 160, and we multiply by pi over 180. Remember that the pi never gets calculated, so it's just 160 pi over 180. And then our calculators, remember, will reduce this for us. So I can just do 160 divided by 180, and then just hit math 1. Enter. 8/9. So 8 pi over 9. So there is our theta in radians, and so now we can use the formula. So the formula is S equals R times theta. R is 10. Oh, I forgot up here. This is 5 pi meters. Need the units there since it gave it to us. This is centimeters. So 10 times theta, which you saw is 8 pi over 9. 8 pi over 9. So what that does is it gives us 10 times 8 is 80 pi over 9. And 80 over 9 doesn't actually reduce. So that's it. 80 pi over 9 centimeters. All right. Last one. Central angle with a radius of 1.25 feet measures 0.6 radians. Okay. Now this one does not have a pi in it, which is it's fine. You can have just numbers too of radians. It doesn't have to have pi in it. Usually it does. So find the length of the arc intercepted by this angle. So this is just sort of plug it in. S equals r times theta. R is 1.25. Theta in radians is 0.6. So S equals 1.25 times 0.6 is 0.75 feet. And that is it. That's a lesson. If you have any questions, let me know. Message me, email me, whatever you need to do. If you have questions, you can come by and see me. There is a big ideas for all this stuff. You can get some practice with it, please. Get some practice with it. This is definitely, we're now getting into, we have 3 sections here at the end that are going to be definitely challenging. So it's going to be definitely worth your while to do the practice problems. All right? Thanks.